We're going to try to cover a couple of sections to get us prepared for a new type of integral. But before we do that, we need to take care of a couple of things. But before we get started with the two sections that we're going to cover, I want to look back at Green's theorem real quick and just take a look at this a little bit more closely, and maybe I'll write it a slightly, backwards way. Usually they write the line integral first, but then they write it differently. So I'm going to write it like this. Q, P, x minus dp dy is equal to line integral of, and they write P dx and Q dy, but let me write it a little bit differently. I'm going to write it with P Q dr, and for this one, I'm going to use a strange notation that hopefully will not be strange later on. And I know we kind of know this as the partial, and so in fact that's what we will denote it as, the partial derivative, when we're looking at functions. But unfortunately, or however you want to look at it, this is the symbol that they use sometimes for the boundary. So I'll annotate this notation, but this is essentially Green's theorem. And let's see if we can break this apart somewhat. So let's first address this idea that this is the boundary. As a notation, this is the boundary. And then what we have here is your vector field. Okay? And so what we have here on the left-hand side is the actual region. And then this, we will learn today in a little bit more detail, is, I'll keep it vague for now, is some sort of derivative. Of that vector field. Now, what kind of derivative it is, we'll, like I said, we'll talk about that in our first section that we're going to cover. But if you look at this setup, there's one more thing to point out, I guess. Here we have a double integral. And here, this is really a line integral. Line integral of a closed curve. We usually put that circle there. But this is really just a single integral. Yes?
Does this theorem work for just closed curves only?
Yeah, the definition, or not the definition, but the statement of the theorem says that you have to be looking at a closed curve. Okay. Because that closed curve has to enclose a region. So if we look at this with a really critical eye, we're saying that the integral of something over some region is going to be equal to the original function. Well, it's the integral of the original function over its boundaries. So it's like going one integral down. So we went from a double integral to a single integral. And we're taking the derivative of something, and then we're essentially finding, in loose terms, kind of like the antiderivative of that, or the derivative of something, and then we come to the original function. And then we take a look at the region that we're integrating over, and we're integrating over its boundary. So if you think about that and compare it to our original fundamental theorem of calculus, we're actually integrating over an interval. So let me rewrite the fundamental theorem of calculus slightly. As integrating over a one-dimensional interval, the interval from A to B, of a derivative of something, and then we get that original function that we're going to evaluate at the endpoints. So if we look at it like this, we have our region, which in this case is an interval. We have a derivative. And we have a single integral. And then we're saying that we're going to evaluate the original function at the boundaries and this time where it's not an integral anymore, you're kind of going from a single integral to no integral. So if we look at it like that, it really is just the fundamental theorem of calculus. Green's theorem is really the fundamental theorem of calculus. So we go from an integral of a derivative over a region to the original function evaluated at the boundaries. Okay? We're going to see two more big theorems like this. They have special names because they're used a lot in physics and engineering. But if we really break it down, it's just the fundamental theorem of calculus. All right, let's move on. So this is just a little wrap-up from last time when we talked about Green's theorem. Now we're going to talk about, in our new section, two new sections, we're going to talk about the derivatives of these vector fields. So in this section, 16.5, I guess, we have this thing called the div and the curl. We're going to study the div and the curl. So these are the derivatives of vector fields. We'll start with the del operator and then the notation and definition for the divergence and curl, and then we'll take a look at some properties. So let's start with the del operator. The del operator by itself is like nothing. It's like plus. You're going to plus something. So by itself, it does nothing, right? What you need is something to put in there, like when you say plus, what are you going to add? So you have to give something to input. A more parallel or a more interesting analogy would be the integral. The integral by itself is an operator. It takes in a function and then spits out another function. So an operator would be something that you would write and leave a blank space for something to put in. So an integral operator might look like this, where there's a blank space for you to put in, and you're going to put in a function. So we can think about the integral as taking a function. Actually, I'm sorry, let me take out the a and b here. The integral is, I guess we normally wouldn't call it a function, we would call it like an operator. We'd take a function and then it'll give you its antiderivative, which is another function. That my little abbreviated notation doesn't look very good there. So it takes a function and then gives you another function. So that's generally how these operators work. And it turns out that these are linear operators, which you can learn from an advanced linear algebra class. But these are just operators. We can think about it. And just like functions, they would take an input and give you an output. So integral would input a function and then would output another function. Well, the del operator is the same thing. It's a function. It's an operator that you put in something and then you get out something else. But what you put in is not, it takes more steps than just, quote, putting something in. And we've seen this, this notation before, this symbol, right? Where did we see the symbol before? We use a symbol for the gradient, right? So we've used the del operator for the gradient. And what we do is we take a function, a scalar function that takes, a two-dimensional into a one-dimensional point, or a three-dimensional vector into a one-dimensional point. And then we said grad f, and then we denoted it by the notation with this operator. And if you look at this operator as a vector and treat it like it was a vector, think about this as a vector. And remember that f is a scalar function, which means it outputs a scalar. If you think about this as a vector and a scalar and apply the scalar multiplication, then this simply becomes the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. So that's how we found our gradient, right? So think about this as a vector operating on a scalar function, and then it would just be like a scalar multiplication. except it's not being multiplied, it's being operated on. Okay? So if we think about it that way, then we have a couple of multiplication operations for vectors, right? Because we're interested in doing some derivative-like things to vector fields, and now this is a derivative vector, kind of. And so maybe we can apply that to a vector field. What are the two types of multiplications that we can do with vectors? So the dot product and the cross product. So we can imagine taking the dot and the cross of this del operator with a vector field. So that's exactly what we're going to do. All right, let's do that. Actually, I think I have it in my notes. So we'll start with the divergence, also known as the div. The divergence is a dot product between the del operator and the vector field. So you take a vector field, which is a vector with components. Each component has a function. And then you operate it using the del operator. Now I guess I skipped a step here to actually show the work. So what you're doing is you're taking d dx, d dy, d dz, and you're dotting it with p, q, r. That's your f. And so when you dot this, the first component is just going to go with the first component, the second component with the second component, and then the third with the third. And then this is all you have. Now notice what the result is here. What is the result there? Is that the derivative? It's a what? It's a scalar. And that agrees with what we did before when we took the dot product of stuff. When we take the dot product of two vectors, we get a scalar. And so, again, this is a function, but it's a scalar function. And with dot products, you could do in 2 dimensions or 3 dimensions. If you're doing this in 2 dimensions, you can just adjust your del operator to just 2 dimensions. Okay? Can you do an example? This is really simple, right? Right. I need a vector field. Let's see. I don't know. 2xy, comma, cosine x minus z, comma, z squared plus yz. I don't know, just making it up. So if we were to do the div of this vector field, you can write it a couple of different ways. You can write it with the actual word div f, or you can write it with the nabla notation. And this is equal to, well, just take the derivative of each of these components with respect to whatever slot it's in. So derivative of 2x with respect to x. So this is going to be 2y plus derivative of this thing with respect to y. There's no y's in there, so that's just going to be 0. Derivative of this thing with respect to z, 2z plus y. And then that's it. And then you get, if you want to simplify this, you get 3y plus 2z But, you know, that doesn't matter. It's a scalar function. It's a function that is a scalar, and then you put values in for x, y, and z. Okay? Yeah?
So, looking again, like a physical example would be like the velocity vector field, and then you have something moving through, and you get a scalar out, and you get like energy or velocity out in space, right?
You get velocity. It's a change in something. And what they're measuring is actually the compression. So remember, a vector field is a field full of arrows, either in 2 dimensions or 3 dimensions. So what happens is that what you would imagine is that if you put an object into this vector field and have it flow towards whichever way the arrow is going, it's going to measure how your object is going to expand or contract. And it's a scalar, so it just a numerical value would do that. So if it's positive, you can see it expanding as it goes through the flow. And if it's negative, then you could see it contracting, compressing. Okay? All right, so that's one derivative. I think I have something. I have to find it. Maybe I'll find it later. All right, the next one is the curl. So we had the dot product, right? And so the other one is a cross product. Now this really works well for 3-dimensional vectors. We don't really have a definition for a cross product of something more than 3 dimensions. And if we deal with 2 dimensions, I think we can work with that. We'll see an example of that later on. But here is the definition of the curl. Now, trying to memorize this definition is not ideal because you got a bunch of partials all over the place. But a good way to remember this is the determinant. It's a cross product, right? What are you crossing? So you're crossing the del operator and the vector field P, Q, R. So if you remember how we computed the cross product before, we kind of set up a matrix and then we found the determinant of 3 by 3 matrix. So up on top is the I, J, K vectors. And then the middle row was the first vector. Now that vector is really just the del operator, right? So d dx, d dy, d dz. And then the last one, the last row, would be the second vector. That's p, q, r. So if you were to do the cross product, you would, at least I would, in the first component, I would take a look at the partial of r with respect to y minus the partial of q with respect to z in the I direction. In the j direction, it would be negative of the partial of r with respect to x minus the partial of p with respect to z. And you see that this is positive, but the 2 partials that I mentioned were mentioned the other way. So you can think about that negative being distributed. And then the last one, the partial of q with respect to x minus the partial of p with respect to y. So I know that's not easy to memorize, but if you remember doing your cross product and how to do your cross product, that's how you would get the curl of something. Yes?
And what would we use curl for? What kind of application?
Well, an application would be to see how things rotate. The curl measures the rotation. In fact, Yeah, I don't know if I'm going to do a good job either.
I think you're going to do a better job than the book. I don't even know if the book mentions anything other than just us finding out whether a vector field is conservative or not.
Yeah.
You can talk about the time force, which can find rotation and less mechanical stuff. So when you think about something mechanically rotating through the field,
Yeah.
doesn't go wrong.
Yeah. You put something on the field and have it go along the flow line and see if it rotates around. And so sometimes this is called ROT, short for rotation, rotation of the vector field. And then notice that your output is a vector. Now, it's a vector. Yeah.
This might be backtracking a little bit. If you go two-dimensional and take the determinant of that, it looks the same as the Green's theorem.
Wow.
And something the curl, like the boundaries of the line integral, it would go into the region of that curl. So extending Green's theorem to R3.
Well, that's what the curl does. In fact, Thomas kind of hit it in the head and then kept on pounding it. I didn't understand the rest of it. So I'm trying to understand what you were saying about the boundary business, and it's not making sense to me right now.
Well, so you have like a boundary in the line integral,
Mm-hmm.
which is just a line
Yeah.
around it,
Yeah.
and this is like the region of the curl, so it can be like it's
Oh.
two-dimensional domain.
Yeah.
So in the double integral, that's also a two-dimensional domain.
Mm-hmm.
So you'd be taking that and it'd be kind of making that one-dimensional line into a two-dimensional region.
Got it. So what he's saying is something that we're going to discuss in a lot more detail when we take this to 3 dimensions. But if you take a look at Green's theorem, first of all, he found this. I was wondering if anybody would figure this. But this last component, if you look at this, is the thing that was in Green's theorem. In fact, if you let R equal to 0, and you assume that P and Q are functions of just X and Y and there's no Z's. So maybe I was going to do this later, but since you brought it up, let's talk about it now. If F is equal to P of X, Y, so it's only a 2-dimensional vector field, Q of X, Y. And then we can assume that R is equal to 0. And we can assume that there's no Z component. If we imagine how that would look like in the curl, I, J, K, partial with respect to X, with respect to Y, with respect to Z, P, Q, and 0 for R. If we take the partials, if we take the curl of this, we see that in the I direction, we're taking the derivative of 0 with respect to Y, and we're taking the derivative of Q with respect to Z. But remember that Q doesn't have any Z's in it, right? So that would be 0 as well in the first component. Now the middle component is a partial of P with respect to Z. Again, the P doesn't have any Z's. And the partial of 0 with respect to the other variable with respect to X. And then all you have left is dq dx minus dp dy. Right? So all you would have is this, dq dx minus dp dy, and then we can just, to write it without the 0, 0 in the bracket form, I can write it with the I, j, k components and just ignore the I and the j because there's nothing. So if we think about this happening in 2 dimensions, this is a special case. Happening in 2 dimensions, what you have is a measure of rotation So imagine you're measuring how things rotate in a region D, right? And that kind of pushes along on the curve, the boundary. So this is C, which in the beginning of lecture today we denoted as the boundary of D with this notation. And so measuring the rotation inside of this is the same thing as finding the line integral of the boundary. Now, how do we measure that rotation? Well, what do we get when we cross something? We get another vector, right? And then when we cross something, we use a right hand. You run your fingers through the first vector and then times the second vector, and then you get a vector that's pointing in the direction of your thumb, your right thumb. And so if you imagine crossing something like this, you're going to get this expression over here, right? So you're measuring the rotation. Now, on a flat surface, if you're rotating on a flat surface, then which way is your direction vector going to go? Either one of 2 directions. What?
Either opposite.
If your domain is flat, the xy plane, which way is your vector going to go? Either up or down along the z, right? And if you notice the curl of this, it's 0 in the x, 0 in the y, and it's directly going up or down depending on whether this last term is positive or negative. So your curl of these things would be going straight up. And if it's going up, then that means you're measuring this in a counterclockwise direction. And if it's measuring in a counterclockwise direction, that's how your boundary should look like. If it's negative, then your contributions will be negative, and so these things would be pointing downward. And that's the opposite of the counterclockwise direction that you have. Yeah, the right-hand rule gives a counterclockwise rotation of which way your fingers are curling. So this thing would be going, the vectors, these vectors that you would be looking at, the curl would be going straight at you, looking at it from the top. Okay? So there's your tie-in. This is, in fact, a derivative. So in the beginning, I said, oh, maybe we'll just call it some sort of derivative of some sort. Now we can come back to this page and say, hey, this is really the curl. Okay? Good job, Thomas. All right, we got the div and we got the curl. Those are our 2 main derivatives that we're going to talk about. They come with properties course, two properties that are big enough to become a theorem. No, battery's not included. Oh, I should have reformatted this a different way, but let's see if we can work with this. So, if you have a gradient field, curl of a gradient field is 0. If you have a gradient field, it turns out that there's no rotation in there. So remember, there was a way for us to check if something was a gradient field. If it's conservative, yeah, how do you check if it's conservative? We took like the partials, right? Partial of q with respect to the opposite, with respect to x, is equal to the partial of p with respect to y. Turns out that if you subtract it, you get 0, and turns out that if you subtract it, that's the last component of your, this is for 2 dimensions. Yeah, it's related to the second derivative test. We assume that p is some derivative with respect to x and q is a derivative with respect to y. So now this is just a generalization. Generalized to 3D vector fields. All we have to do is take the curl. Now, granted, taking the curl is not the easiest thing to do. But if it's a choice between that and integrating to see if it actually makes it into a vector field, then I don't know, maybe the curl isn't too bad. Okay? So I'm not going to prove this, but let's see if we could take a look at this and see if we can prove this. The div of the curl of a vector field is 0. So let's take f first. And let's take the curl of that and then take the div of it. So I'm going to switch notations on you just so keep you kind of alert. Remember that the curl is saying it's the cross product of the del operator with the vector field. And then, well, instead of trying to do this with a 3x3 matrix, I'm just going to see if I can remember it. I think it's derivative of q with respect to z minus the derivative of r with respect to y, and then the derivative of p with respect to z, and then with a negative in front makes that into a negative, and then the other one's a derivative of r with respect to x, and then the last one is dq dx minus dp dy, which is the last component. So I just essentially took the formula from the previous page and just recreated it here. Now I want to take the div of this. which means I have to take the derivative of this thing with respect to x. I don't want to put a vertical line. I'll d dx, d dy, d dz, and then add it all up. So a little bit more room here. So the derivative of this thing with respect to x, how am I going to write this? You guys know that the notation for this kind of goes backwards, right? It's going to be d squared q dx dz, and then it's important to note that you took the derivative with respect to z first, and then with respect to x, minus d squared r dx dy. And then this is, the div gives you a scalar, so in place of commas I'm going to have an addition sign, and then tediously write out the rest of this. And then the last one, d squared q dz dx minus d squared p dz dy. Now, I guess I don't know why it mattered, because if these are nice continuous functions with second order derivatives existing, then if you switch the order of integration or differentiation, it should still be the same. So if I look at d squared q dx dz and d squared q dz dx, that these two should actually be equal to each other. Uh-oh. One of them should be a negative. First two are wrong? Oh, man. What? Sorry. I'm going to change my corrections and make my corrections in green. So this sounds like it should be like this. Is that what you're saying? I should have just copied the, the formula on the previous page. Sorry about that. All right, now back to this. We should see things canceling out. So these two would cancel, the dRs with the x and the y. Should cancel. And then the dp's with the y's and the z's should cancel. So this is how I used to do my algebra. When I have like terms, I would underline it single, double, triple, or whatever. Some people put circles and squares and triangles and stuff. But I see these cancel, these two cancel, and then the last one cancels. And then this turns out to be 0. So this is our proof. Now, I want you to look at this. Yeah. Haven't we done QED in this class? Quod eris demonstratum. It's Latin for that which was to be shown or demonstrated to be proved. What? Well, you say it after you complete an argument, and then you drop your pencil. So, anyways, I want you to look at the zeros. Purposely written. One of them is a 0 scalar, and the other one's a 0 vector. So when you're taking divs and curls and gradients of things, it is kind of important to figure out what your results are, whether you have a scalar or a vector. And then putting the appropriate, I know 0 is a 0, but a 0 vector is significantly different from a 0 scalar. And so you should, when you're doing divs and curls and mixing up the divs and curls of things, you should know your result as a vector or a scalar. Well, it turns out that you can't take a curl of a scalar, for example. You can't take a div or a curl of a scalar. In fact, there's this, I was going to do one of those worksheet things again today, but I didn't think I was going to have enough time. But one of the questions I was going to give you was a set of these combinations of divs and curls. Now, it turns out that these are examples of things that may or may not be legal. And if they are not legal, then you can't perform them. Like if f is a function, f is a scalar function, then you can't take a curl of a scalar function.
No, what I'm saying is for the 0 vector.
Oh, what about it? Oh, if it's a 0 vector, then you have to know that it was a vector, even if it's just equal to 0.
So it's just knowing what it was.
Yeah, knowing.
Rather than what you do with it, you can't.
Yeah, but you can't do anything with it. And grad f is something that you can do. Grad is a gradient. The gradient of f is something that you can do, and this results in a vector, right? It's a vector of partial derivatives. So this here is a good exercise that we're not going to do in class, but I encourage you to take a look at it because, you know, it might come up on the test or something. And then try to figure out what's a vector, what's not a vector, and which one of these are even possible. So this is in the exercise section of your textbook, number 12, apparently. Yeah. The div, no. The div acts on a vector field. The gradient gives you a vector of partial derivatives, which we found out is, you know, would be a good way to help us find our normal vector and stuff like that.
Or R3 0. Has 3 attributes, but all of them.
And they're all 0, yeah. All right, let me see if I can find my little Mathematica program. Lectures? Div curl? Anything? Nope. I'm in spring 2015, 2016. Turn notes. Div curl, nope. 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 Where is it? All right, one more shot. All right, I can't find it. Oh, I'm still looking for it though. Just wasting time. Come on, Ray. Be done. Done. Let it go. I can't. I'm gonna go nuts. Oh, could this be it? So this is just a silly example in 2 dimensions. Where you would see what would happen to an object in 2 dimensions if it would to go through a flow line in a vector field. So our vector field here is a simple x comma y, which is just, you know, those things, arrows, you just go outward. I don't have the vector field. But if the path that you would follow if you drop something, if your vector field just goes outward, if you dropped an object, it would just go outward away from the origin. And as it goes out, it begins to expand. So let's see, what's the other path here? Oh, stop working. Come on. All right. The curl is even cooler because it goes around in circles. I'm wasting time. That was a good 7 minutes already. I don't know if you could do something like that. I think it's the idea is just a point object that something is going to happen to them.
Right.
Yeah. So I think for the curl, the interesting thing to do is to drop a square paper on something that's going around, and so on a lake or something like that. And if there's some wind blowing or something, if you drop this square paper, let's see if it actually rotates around, then that particular flow has a rotation or a non-zero curl. All right, we're going to have to let that go. So back to our. We have one more thing to talk about here, but I don't know if it's that important. And the last thing to talk about was supposed to be Laplace stuff, but I don't have it. Yeah?
Sort of clarification of the del operator is essentially not the gradient if you use it on the function problem. But if we use it on the vector field, that's what it's the divergence.
Not quite. The del operator is nothing until you apply it to something. If you apply the del operator to a scalar, then you get the gradient. If you apply the del operator to a vector, well, there's two ways to do that. One way is to take the dot, that's where you get the div, and the other way is to take the cross, and that's when you get the curl. Okay, so I guess we could try to summarize that. Yeah. So we're basically acting on either a scalar or a vector. And then we could take the gradient of that. Actually, we can't take the gradient of a vector, but we could take the gradient of f. We could take the div. We can't take the div of little f, but we can take the div of a vector field, capital F. And we could take the curl of capital F as well. And so these are the three basic operations that you use with the del operator. Now beyond this, you can combine things as long as you know what your outputs are. And we know that when we take the gradient, we get a vector. When we take the div, we get a scalar. And when we take the curl, we get a vector. So from here, you can think about taking the curl of a curl. Does that make sense? Well, the curl of f is a vector, and you can certainly take a curl of a vector, so that makes sense. Can you take the div of a div? So the div outputs a scalar, and you can't take the div of a scalar, so no, you can't take the div of a div. Div of a div. And can you take the grad of a grad? Well, the grad is a vector, and you could take the grad of that again. And then now, can you take the grad of a div, or the div of a grad, or a div of a curl, or a curl of a div, or a grad of a div, or a grad of a curl, or a curl of a grad? There's not that many combinations. So that's a good exercise for you to think about. And if you could say it really fast, record yourself. Okay?
Extend the concept of vectors to scalars by vectorizing it such that every component just equals the...
You could equal to that same number.
Kind of what a zero vector is.
Yeah, but if you say, if you have 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, then you're just stuck on one line in 3 dimensions, or 2 dimensions. Anyways, let's move on. It's okay. What's this section? What was section did we just do? All right, we got like 5 minutes to do this next one. I've hinted about this idea before. We have a way to parameterize curves, but now we want to be able to talk about parameterizing surfaces. So with curves, you have a function or 3, or I guess depending on whether you're 2D or 3D, you get a set of equations with one parameter t. And then you give it a starting and end point for t, then you can draw your curve. Okay? Now, I hinted at the fact that if you have more than one parameter, if you have 2 parameters, then you can actually parameterize a surface. So let's think about a surface parameterization. This is kind of weird, but think about a surface parameterization as a function, a mapping, from something that's 2-dimensional to something that's 3-dimensional. And a lot of times I call this capital phi. I think the book calls it R. I'm a little afraid to call it R because we use R for our curve parameterization. And so I'm going to see if I could just stick with capital phi and then change it when it's convenient. But what happens here is that, and maybe what you can do is imagine just a piece of paper, or maybe one of those rubber things, flat rubber piece. Do you guys know what I'm talking about? Like a yoga mat, but more stretchy, and things that you can stretch. A plain, flat piece of something that you can stretch. And imagine taking that flat piece of something that you can stretch and curve it and stretch it in one direction and do something with it. Then there's a possibility of you making a surface out of it if you can make it still, make it stay still. So what happens is that you get to shape this any way you can to make it look like a surface. And it would all come from something flat. And what's interesting to look at is, depending on how the surface is cut up, you're going to be able to see the grids on the surface. And you're going to be able to see how things are formed. And I just want to show you a quick example using the program here, where I'm going to try to recreate a sphere, or at least a hemisphere, and then talk about how that would look like. So I would need a graph of a parametric surface. Now, the parameterization for the surface could be with any two variables you want. In a lot of programs, they use u and v, but realistically, you can use, some programs use s and t, but you can use anything you want. So I'm going to do a circle where I just imagine the circle as being x squared plus y squared plus z squared is equal to 0, or is equal to 1. And then I change the x's into u's and the y's into v's. And then I would have it maybe graph from 0. What's wrong? What's wrong? X is not recognized. Oh, yeah, because I wanted u's and v's. Oh, come on. And let's go from -1 to 1. And let's do steps of 20 for now. And we'll talk about the steps in a minute. So you can see that there's because of the domain is a square domain from -1 to 1. It gives me a square domain here, where if it doesn't make sense, if I put 1 in for u and 1 in for v, this is going to be 1 minus something bigger than 1, 2. and you can't take the square root of a negative number, so they just plotted 0 there for some reason. And if you look at how the grid marks are, they're square grid marks. And you can tell which one's the x and which one's the y, mainly because it says there. But if I make this into just 5 steps or 5 partitions, you can see that 1, 2, 3, 4, 5. Along the x-axis, I've only partitioned 5 times. Okay? Like this one, 9. And then this is, if we cut this to 9 also, you know, it's a way to break things up. Now let me parameterize this a different way. And let's see if you guys are familiar with this parameterization. cosine u, sine v, sine u, sine v. What's it look like? What? No? What? What? I heard somebody. Spherical. Looks like spherical coordinates, right? Except instead of ph's and thetas, I'm using u's and v's. So let's see. 2 pi, 2 pi. Maybe I don't want to go. My u is my theta. My v is my phi. So let's go to pi over 2. And if you look at the way it's graphed nicer. I don't have those tails on the corners. And if I break this down, so remember that my theta is the measurement around. So if I let my theta go around, this is going to look really bad, but if I make it go around 10, it goes around here with, it's going to have 10 partitions. I mean, make it look really silly. If this is 5, then it's going to kind of look like a pentagon because there's only 5 partitions that it has. So the more you have, the finer it's going to look. And then on the other hand, phi is a measurement from the positive z-axis down. So if I have 2 of them, those are my 2 measurements from 0 to 1 in the middle and 1 down. And then if I add another one, 3, then it looks a little bit better, but the more you have, the better it's going to look. So I think 10 might be good enough. And then here it looks like a sphere. All right? So the best way to really get into this is to play around with graphing programs. It's hard to just write equations and imagine how they're going to look like. You can if you want. People have done it before, graphing calculators and computers. But to make things easier for you, I suggest that you get into a program like this and try out some of these things. Okay? Tomorrow we'll talk a little bit more about them, and then we're going to integrate over them. All right. Good luck.